All right, let's move on to the second topic that we cover in detail in this course, which is the machine level understanding of programs. So low-level understanding of computers and programs are essential in many fields, like we discussed already. So in fields like hardware development, operating system development, or fine-grained performance tuning, and etc., we often run into a situation where we need to go deeper than the higher level human readable code. So reverse engineering, the term reverse engineering refers to uh, kind of extracting the logic of the program, only looking at the binary where source code is not given. So this is obviously useful in situations like malware analysis, or if you're debugging your code at the low level, or you're especially if you're trying to write a software attack and defenses and so on. All right, so before we delve into the topic further, let's define the terminologies first. So when we say on architecture, when you say architecture, it can also mean the ISA or the instruction set architecture. So this means the parts of a processor design that one needs to understand or write assembly or machine code. So in this architecture, or ISA, defines what instructions are defined or what instruction does what. It also defines a set of registers that can be used by the instructions and so on. And then there's another similar term, which we say, when we say microarchitecture, it actually refers to the implementation of the architecture. So these uh, include basically the circuit, how we're gonna build the circuit according to the architecture. So things like cache sizes, the internals, core frequency, all of these are examples of microarchitecture features. And when it comes to code forms, we call machine code as the byte level programs that a processor executes. And we say assembly code uh, to refer to human readable text representation of machine code. So regarding the differences between architecture and microarchitectures, we can explain it using the commonly available ISAs. So for example, Intel is possible in server and desktop markets, and Intel has this x86 architecture. But if you're interested in building your own PC, you probably know that AMD also makes the x86 processor, right? So Intel and AMD both make x86 processors. So in this case, the x86 64 is the architecture, whereas the Intel or AMD's own implementation of the architecture are called microarchitectures. So, for example, Intel 12th Gen i7 microarchitecture is an implementation of the x86 64 architecture. So ARM is another very popular architecture that has a dominant market share in smartphone or mobile markets. So ARM is also an ISA or an architecture, whereas there are multiple implementations of it. So, for example, Qualcomm makes ARM processors, right? Snapdragon something something. Those are the Qualcomm microarchitectures that are made based on the ARM architecture. Apple also makes ARM architecture, uh, ARM architecture processors. So their microarchitecture implementations are, for example, the M1, M2, the M series of the processor. So an ISA defines how CPU is controlled by the software. So ISA is basically a protocol between the machine code, the your program and the CPU. So there are a predefined set of commands that can be given out to the CPU to perform certain actions. So for example, a CPU can have an instruction called add that tells the CPU to add register 1 with register 2, and so on. So instruction set is kind of a bridge between the software and hardware. So because we have this kind of a standardized protocol, the programmer and compiler together know how to convert the human readable source code into directly executable machine code. So it's a set of commands or uh, and other protocols that allows us to know how to control CPU to achieve general computation. So when you say ISA itself is just a specification and documentation. In itself, is not a piece of hardware. The specification allows hardware makers to make hardware or microarchitecture for the ISA, and system software makers make compilers and linkers for the ISA. So like we already mentioned, there can be vendor-specific microarchitecture for the same ISA. So M1 processor is a microarchitecture implementation for the ARM ISA. All right, so the compilers and the compilation process has a very close relationship with the ISA and the human readable source code. So the compilation process is a process in which source files are converted into executable machine code. So source files written in, for example, C or C++, go through multiple stages during compilation to finally yield a executable file. So if you're using Windows, an example of executable file would be something like a.exe or b.exe. So these are executable file that came out as a result of a finished compilation, and it is ready to be executed by the CPU and the operating system. So we're gonna skip all the details here. And so compilers are software that converts high-level source code into machine code. So if you give it your source code, it'll convert your code into machine code, and this is the assembly format that is a text representation of the machine code. We're gonna skip all these details. All right, so this is a general overview of the assembly and machine code view from a programmer or compiler perspective. So in any modern computer architecture, we have a small register. So register is a small temporary space that are inside CPU that can store data from memory temporarily. So we have a very important register or a component called PC. So PC stands for program counter. So PC always stores the address of the next instruction to be executed. So given a code like this, so these are all commands to the processor. You want to add, subtract, jump, and so on. So PC is something that points to the address of the next instruction to be executed. So PC will be advanced every time you execute something. It'll constantly move as the processor executes to point to the next instruction to be executed. So this PC is called the RIP on the x86 architecture. So register files are heavily used program data. So it's a space for uh, temporary data to be stored inside CPU. So it's kind of like similar to having a fixed number of variables. So, and also we have special types of storage called condition codes. They store the status information about the most recent arithmetic or logical operation. So this is used for conditional branching, such as if, else, or while, or for loops in terms of C terminology. So these store the result status information from computations so that we can make decision as to which block that we're going to execute depending on the condition that we have usually have inside the if statement. All right, so this is the assembly code. So we're looking at machine code stored in memory addresses inside memory. And this is the text representation of the code. So number one is the memory address of the stored information. And number two is the byte code that represent the instruction. So these are zeros and ones that form a certain command that is to be given out to the CPU. And number three is an assembly language representation of the instruction. So these are the types of commands, and we call this the opcode of the ISA, and this dollar sign zero or percent sign EAX are the operands, where the dollar sign denotes constant and the uh, percent sign denotes a register. So PC always stores the address of the next instruction to be executed, and it constantly moves as we finish one instruction and another. So registers are temporary spaces for storing the currently processed data fetched from memory. So the number of registers are fixed. So these are the integer registers that are available on x86. So these are kind of like the fixed variables. It's kind of similar to having a fixed variables in C programming, where we can temporarily store and process data. All right, so memory. So memory, these are the RAM sticks that we put it into our PC. We all know that memories store data. So memory is kind of like a byte array that is theoretically 2 to the 64 addressable bytes in 64-bit computers. And each location of the byte is what we call as the address of the data of the byte. And when we store the address into another memory location or in a register, we usually call it a pointer, right? So pointer PTR of another variable, then we are storing this memory address into another location, which we commonly call pointers in C or C++ programming concepts. So memory stores code data from the program's executable and other components such as heap or stack. So here are some assembly characteristics. So integer can represent either 1 byte, 2 byte, 4 byte, or 8 byte data. So it's not difficult to see that, these are char, short, int, and long bytes. It can also store addresses or pointers, which are 8 bytes because we're using a 64-bit systems. So one thing that you're going to learn in this course is that the C programming language, although at first sight seems very difficult, it's actually a very thin abstraction level over the machine level execution. So the reason why we have char, short, integer, long is because not because someone just made it up, is because that's the sort of a fixed width of data that CPU can work with. So that's just an abstraction over the data sizes that the CPU can handle. So yeah, and other questions that you might have regarding the C programming language is probably because it's just a direct abstraction over the low-level stuff. So questions like why does C programming language support only one return value? Well, this is because how CPUs are made to support function execution. And why do we use pointers and why do we have to deal with pointers? And this is because, I mean, that's how uh, processors work. So these assembly instructions have the following characteristics. So in terms of operation, these commands to the CPUs perform very small operation at a time. So it performs arithmetic function on either register or memory data. So it transfers data between memory and register. For example, it can load data from memory into register or do the vice versa. So it can perform things like transfer control, things like unconditional jumps from different places. It can also do conditional branches. So these are the operations that vary performs one small task at a time. Uh, so these are combined to form some kind of logic, which can eventually form functions, and functions eventually form a full program. So we're going to start looking at machine instruction example. So what you see at the top is a one-liner C code. So what's happening here is that we're trying to store value t into a memory location designated by dest. So dest is a pointer, it looks like. So it looks like a integer type pointer. And in assembly, it is equivalent to something like this. So we have move instruction that moves t. T at the time of this execution is stored in a register RAX, and this is being copied into a memory location pointed by RBX. So we can see that the data stored in RBX is a pointer type. And when you have this parentheses around the register in this x86 assembly notation, it means that the value stored in the register is to be used as a pointer. So this is not just a register to register movement. This is a register to memory operation. So we're moving 8-byte value to memory with this instruction. And this instruction is stored at this memory address. So The instruction itself is also a bytecode sequence. So CPU interprets this data, and from CPU's viewpoint, it sees move RAX, RBX. So this is a 3-byte instruction that performs a single register to memory operation. So GDB is the name of a debugger tool that we're going to use in this course. So if you ever take this course, then we can use this tool GDB to disassemble, meaning converting this machine code into human readable assembly form to examine its behavior. So you can do this on any binary programs out there. Actually, in this course, we do a lab assignment where you're given a binary program without a source code, and your job is to figure out what the given program is doing. So you're going to be doing this really interesting reverse engineering test if you take this course. So moving further into, so we're going to do a quick preview of what programs actually look like at the machine level. So we're going to skip all this, and we're going to look at different possible combinations of operands with this move instruction. So move instruction is a very powerful instruction that can perform various operations depending on the operand type. So we have 3 types of operand here. So the first is called immediate. So for example, if you're doing something like this in the C programming language, this is considered a constant, right? So it's a constant value. And to implement this type of variable, this type of value load, we use the immediate type. So for immediate constants, these numbers are encoded directly into the machine code without getting loaded from another register or another memory location. So we can also have a register type of operand. So we already seen the list of registers that are available on x86, right? So by using these registers, we can temporarily store certain information. We can also use registers to move certain data. Sometimes we move the data in and out of the memory and so on. So these are the possible combinations. So you can go from immediate to register that would achieve load RAX with 4. In C, it'll look something like this. And you can also do immediate to memory, which is equivalent to this, loading a certain memory location with a pointer or with a constant. Of course, you can do register to register movement, which is similar to assigning one variable to another. And memory, of course, you can deal with memory, as we already saw. You can store certain information into memory, or you can bring the memory back into the register, as you can see in this case, and so on. So we're gonna skip all this for simplicity, and we're gonna examine this example so that we can better understand how machine code can implement a very simple C function. So take a moment to look at this C code shown here. So this is a very simple function, right? So it takes 2 long pointer types, and what it does is it's going to swap the value, meaning the memory location pointed by XP will now store the value pointed by YP, and YP will now store the value of XP. So let's take a look at these instructions line by line. So since all of you are seeing the assembly code for the first time, we're gonna take it really slow, and we're gonna learn how the program executes at the very low level, looking at this animation. All right, so these two pointers that are coming into the function as arguments are stored in the RDI and RSI registers respectively. So the values that are initially stored in these registers, the XP and YP, these store the addresses to the memory location. So XP points to address 120 and YP points to the memory location 100. All right, so let's execute the first line, the very first line. So in this instruction, what we're doing is we're loading the value from memory into register. So the memory location pointed by RDI is being loaded into RAX. And in the next example, 456 at the location pointed by RSI is being loaded into RDX. And then what we're going to do next is that we're going to swap the values. So the value in RDX will go into address 120, which is stored in RDI as a pointer type. And the subsequent execution, we're also going to store 123 in address 100. So as a result, we just swap the value in memory using only 4 move instructions. And these instructions in a sequence implement this C function. All right, so we're going to skip this part. So yeah, we can implement. So the move instruction and similar instructions support this form of more complex address computation format, which is written in this notation, D, RB, RI, and S. So these together form various types of address computation forms. So in the first example, using RDX as a base, we want to access the base plus 8. You can also use two registers. One is used as a base, one is used as an index, and it together forms F000 plus 100. So RDX RCX4, this implements base plus 4 times index, where 4 is used as a scale. So you might think this is kind of a random address computation format, but if you think about it, you already seen this kind of computation already. So let's say we are working with integer array like this. And let's say we're trying to access array index number 4. So why am I talking about talking about this array all of a sudden? Well, it's because this computation form is quite frequently used to access an element in an array. So let's say this array pointer is 0xf000. And what is the size of integer? It is 4 byte, right? So each integer element in this array have a size of 4 byte. So to access an array, integer array that has this base address and location of index of 4, the address computation form comes out to be 0x f000 plus 4 times 4. So that would be the address of this array index location. So this is basically a high-level abstraction over the conventional pointer or array calculations that you already do in C, right? So again, this shows how the high-level abstractions like array or pointer, arithmetic, all of those C abstractions are actually a very thin abstraction layer over how computers actually access memory by calculating their addresses. So take a look at this example. Given a program, simple program that looks like this, how do we calculate, how do we move data out of memory and into the EDX register so we can start computation? So this first variable is stored in RDI, and the second argument is inside RSI. And you're going to see that this operation in C is equivalent to this assembly instruction. So basically, we're doing integer array plus index times 4, where the size of this size 4 is size of integer. So we're going to skip through and so yeah, of course, there are other instructions that can be used in the x86 architecture to form arithmetic computations. And what we do in this course is that we're going to take a look at a C code example and then its assembly version, like we just did. So by looking at how C code are compiled into assembly and learning how logics can be formed using this very small piece of logic, which are instructions, we kind of try to achieve better understanding of how programs operate on the processor themselves. So yeah, this is a bit more complex example. So we're not gonna go through this example. This is too complex, but by looking at how C code can be translated into assembly by combining all these instructions together. So learning assembly, of course, is not that straightforward. So you're gonna run into some weird behavior, unexpected discrepancies between the C code and the assembly. This is because the C code to assembly translation is performed by compilers, and compilers are very, very complex piece of software that is really specialized in optimizing your code. So therefore, the C code that you write is more focused on expressing human understanding of the logic, right? So it's not always in the optimized form. It is more geared towards human understanding, and so you want to write a code that can be understood and maintained by human beings. On the other hand, at the low level, the number one priority in compiling C code into assembly or machine code would be efficiency. So you want to yield the most efficient code possible. That's one of the reasons why the assembly code is not like what you expected from the human readable C code. So we're going to be looking at those examples and understand what kind of optimization strategies that compilers provide to yield the most efficient form of the machine code. So it'll be a really interesting topic. So if you ever take this course, I'm pretty sure you're gonna enjoy it. So we're not gonna obviously cover the details here, but another thing that we cover in detail in this course is how we can support uh, higher level abstraction, such as the notion of having functions and having a chain of function calls. So programs are usually composed by chaining multiple function calls, right? One function calls another, and that function calls the other one. Then the function returns as it finishes its task, and then the caller function continues execution. So program execution is always a chain of constant function calls, returns, calls, and returns, so on. So the processor, the computer processor support for that, for such relation between function calls are usually achieved through what we call stack. So stack is a special type of data structure uh, that supports two operations, so push and pop. So you're going to be learning how things like function calls, return values, those can be implemented using the assembly code. So it gives you a better understanding of how your C code actually runs, how procedures are abstracted by the C, and so on. So we're going to skip all this. So one really interesting lab assignment that is given this course is called Attack Lab. So Attack Lab gives you a chance to experience what it feels like to be a hacker, basically. So you're going to given programs with software bugs, and your job will be to write a attack code for the given software. So software attacks are made possible through exploiting the software bug. So all programs have mistakes and loopholes, right? So if you make a mistake, so C is notoriously difficult to make right, especially regarding the use of pointers. So if you make mistake in using pointers in C, there's a very high chance that the program will just crash, right? So this is when you see errors like segmentation fault and so on. But if you have low-level understanding, for example, you have taken system program at SKKU, if you have enough knowledge and some amount of creativity, you can exploit the software bugs to your advantage. Meaning you can maliciously trigger the bug and control the program behavior from that point on. So this is called the software exploitation. So this is what people usually call hacking, right? If you hack some computer in the some software in the server, you uh, take advantage of the loophole in the software, you get into the server. So this is called software exploitation. So if you take this course uh, with the low-level knowledge that you have obtained, you should be able to understand and also write your own attack code. So that's what this lab is about. So it'll be really interesting, and you should be able to write code that attacks software. So you probably heard of the term Stack Overflow already, right? Stack Overflow is this website where developers ask questions to each other. You can also sometimes copy your homework from the website, right? So the term Stack Overflow comes from the very common stack buffer overflow bugs that can be found in many C programs. So in the attack lab, the lab assignment that you're going to be given, your job would be to exploit stack buffer overflow. So, by the time you reach this point of the semester, you should have a very good knowledge of how computers work and how stack is managed by the uh, processor. And also, you should be able to spot a weakness in the program and attack the vulnerability. So right now, we can easily spot the vulnerability in the code on the left. Uh, so you can attack this vulnerability to inject malicious code to cause stack overflow and also take the control of the server. So this is what this lab is about. This is also sort of like the finale of the course. So by the time you understand how machine code works and how uh, code runs on the CPU, you kind of complete this chapter by learning how to write attack code against vulnerable software. So that's it for this overview. So overall, this course provides intuition into how programs work and uh, how you can optimize programs, and also you can also learn about the uh, security side of the software. So overall, I would really recommend this course. If you have any questions, please do not hesitate to send me an email. All right, then until next time.